This is section 8.2, and we are going to be graphing functions now in the form f of x equals ax squared plus c. So in 8.1, we were just graphing f of x equals ax squared. So now we're just adding on some constant at the end. So I copied and pasted this example 1 from section 8.1, and I just want to talk about this and relate it to what we're about to get into today. So in 8.1, you were graphing functions that were in the form y equals ax squared, and a vertically stretched the graph if it was greater than 1, or it vertically shrunk the graph if it was between 0 and 1. So if this was a 1/2, then all your y coordinates were half the distance towards the x-axis. If this was a 5, then all your y coordinates were 5 times the distance from the x-axis. So vertically stretching and shrinking away from the x-axis. So today, again, the difference is we're going to tack on some constant at the end. We'll add some constant at the end. And what's going to happen if we do that is, so let's say there was a plus 2 out here. Well, because of the order of operations, you would have to evaluate the exponents, so the x squared part first, then multiplication, so you'd have to multiply by the leading coefficient, and then you would add on the constant at the end. So what would happen is all of these y coordinates would be increased by 2 units. So instead of a 9, you'd get an 11. Instead of a 4, you get a 6. Instead of a 1, you get a 3. Instead of a 0, you get a 2, and so on. So all your y coordinates get increased by 2 units if you're adding 2 out here. Well, what's going to happen then is all of your heights are going to be 2 units up. So that's going to cause a translation up 2 units. If this was a 7, it'd be a translation up 7 units. So if you had a -5, it'd be down 5 units. So that's what we're going to work on today. Some other things that we're going to look at today are characteristics of our graphs. Because we can now translate up or down, we're going to have graphs that cross the x-axis. That was a poorly drawn graph. We're going to have graphs that cross the x-axis. So now we can actually find some x-intercepts. So we're going to focus on that today. We're also going to talk more about that axis of symmetry, which again is the line that cuts the graph into 2 equal parts. So that's going right down the middle here. It's still the y-axis. And I think that's all we're getting into today. If I miss anything, we're going to cover it. So here we go. Remember, this is the parent quadratic function. So that's never going to change. This is always the parent quadratic function. F of x equals x squared. So if I tell you to write any transformations or compare to the parent function, you're always comparing back to this, and you're comparing to this graph. All right, let's get into it. So as I was saying, with this section, we are going to be adding on a constant at the end. Now, you can take a look at this. It says if a is greater than 0, your graph could look like this, where it's opening up, but it could be translated up or down c units. So if c is a negative, that means that c is less than 0. So if you're subtracting something, the graph gets moved down, translated down that many units. If c is greater than 0, so if you're adding some positive, c is translated up that many units. It's the same thing here. So this one just says a is less than 0. So now your graph is reflected over the x-axis, so it opens down. But it's still going to get translated up c units if c is a positive, or down c units if you're subtracting some number. All right. So because it can get translated up or down, the vertex of the graph, remember the vertex is just the highest or lowest point. I should write that on here. The highest or lowest point of the parabola. And it doesn't have to be a parabola, so I should say of the graph. The vertex is going to get translated up or down with the graph. So if you translate up c units, well, now your vertex right here is translated up c units, so it'd be 0c. If you go down c units, then 0c is still going to be your vertex. So in the previous section in 8.1, it was always at the origin. It was always 0, 0. But today it could get translated up or down c units. So your vertex also gets moved c units. So 0c is the vertex. The axis of symmetry is not moving anywhere because we are not going to be shifting left or right today. We're not translating left or right. It's just up or down. So the axis of symmetry is still x equals 0, which this is just the y-axis. So x equals 0 is the equation to the y-axis. Right. And then here, some new vocab. Zero of a function. A zero of a function is just an x-intercept of the graph of a function. So with a parabola, you can have 1 0, 0 zeros, or 2 zeros. So I'm just going to draw some examples. If we were in class, I'd have students go to the board and give these a try. But the 2 zeros option. So if I want to draw a parabola that has 2 zeros or 2 x-intercepts, what I'm going to do is draw a parabola that goes through the x-axis. So that has 2 zeros. So here's 1 0, and here's the other 0. All right, let's try the next one. If I want 1 0, well, that just means it's going to hit the x-axis one time, and then it could go up or it could go down. It doesn't matter. So for this one, I'll just go down. There's 1 0 and the 1 x-intercept right there. And then no zeros. So that means you're not crossing the x-axis at all. So either you've translated up and your parabola is going up here, or you've got a parabola with a reflection over the x-axis and you translate down, so you're down here. So it doesn't matter, again, up or down, we could have either option today, but I'll just draw this one going up. So that one has no zeros because there are no x-intercepts. No x-intercepts. There we go. All right, so example 1 in section 8.2, what we're going to be doing for this one, it says find the vertex. Remember, the vertex is just 0, c. So this is y in function notation, y equals ax squared plus c. So I could put a little plus sign in here, plus c. So this guy right here is c. So if my vertex is 0, c, then my vertex is 0, negative 4. So again, this translates the graph down 4 units, so my vertex gets translated down 4 units. So instead of it being at 0, 0, it's at 0, negative 4. So we already have a point on the graph right there. I mean, you could plug in 0, that would cancel this out, that'd turn into a 0, and then minus 4, you get out negative 4. So 0, negative 4, again, that's the vertex. All right, find the vertex, done. Graph the given function, and then compare, again, means find the transformations from the parent function. So to graph the given function, we will still use the XY table. For those of you that, I could tell this when I was looking at your assignment, some of you are already using that parent function. Remember the parent function, you'd start at 0, 0, you go right 1 up 1, left 1 up 1, right 2 up 4, left 2 up 4, right 3 up 9, left 3 up 9. Did I count the right? 1, 2, 3, 4, 5, 6, 7, 8, 9. One too many. So some of you are using that parent function, and then instead of going right 1 and up 1, because this is a vertical stretch by a factor of 2, you went right 1 and up 2. Instead of right 2 and up 4, because of the vertical stretch by a factor of 2, you went right 2 and up 8. So I can just tell, because some of you didn't need those XY tables, that you are just using the parent function and graphing. I did the same thing on this side. There we go. All right, so you could do the same thing here. It's a vertical stretch by a factor of 2. So from the vertex, instead of going right 1 and up 1 like the parent function, well, it's a vertical stretch by a factor of 2, so go right 1 and up 2. Instead of left 1 and up 1, you go left 1 and up 2. Instead of right 2 and up 4, you go right 2 and up twice as many, you go right 2 and up 8. So you can still graph using those transformations. It will still work. But if you're not comfortable with that, that's okay. I can still make the xy or this xg of x table. So what I'm going to do is plug in values to the left and to the right of my vertex. So I'll plug in -1 for x, I'll plug in +1 for x. I already know when I plug in a 0 that I get out -4. So if I plug in -1, +1, let's go with 2, 3, -1, -2, -3. All right, so if I plug in a +1, follow the order of operations. If you don't follow the order of operations, let's say do 1 squared, subtract 4 first, and then multiply by 2, you're going to get the wrong value. So follow the order of operations. You have to do exponents before you multiply, and then multiply before you add and subtract. So here, if I plug in a 1, I get 1 squared is 1, times 2 is 2, and then 2 minus 4 is -2. If I plug in a negative 1, when I square a negative, it becomes positive again, so I get positive 1 times 2 is 2, minus 4 again is negative 2. If I plug in 2, I get 2 squared is 4, times 2 is 8, minus 4 is 4. I'll get the same thing when I plug in the negative 2. If I plug in a 3, I get 9 times 2 is 18, minus 4 is 14, and I'll get the same thing with the negative 3. Okay, so now I need to graph my points, so I get negative 1, negative 2, positive 1, negative 2, 2, 4, negative 2, 4, and 3, 14 and negative 3, 14 are off my graph. So I'll just graph here, draw my parabola again. Some of you on your homework are just doing this, but that's definitely a V-shape, right? And that's V-shaped graphs are the graphs of absolute value functions. So please try your best, try to make it look like a U. Remember, parabolas are U-shaped graphs, and all of these quadratic functions are parabolas. So try your best to make it look like a U. I mean, I'm drawing with a mouse, so that's not easy, but it should have some curve going on down here. Try your best, see what you can do. All right, and this is the graph of g of x. All right, and lastly on these problems, it says compare to the parent function. So I'll list out the transformations. So my first transformation right here, that a value is still going to be causing the vertical stretch or shrink. Because it's greater than 1, it is a vertical stretch by a factor of 2. Make this a little bit smaller. Vertical stretch by a factor of 2, meaning it's twice as tall, which makes it narrower. Format this real quick. All right, and then the minus 4 out here is going to be causing a translation down 4 units. So now it's all shifted down 4 units. On this example here, we have an extra transformation going on, but for this one it says first find the vertex. Okay, so again, the vertex is 0, C. Here is your C value. It's a positive 3, so the vertex is 0, 3. And then to list the transformations, we have instead of a vertical stretch, because 1/2 is between 0 and 1, this is a vertical shrink by a factor of 1/2. And again, it should be a positive 1/2. It's 1/2 as tall. That's what that means by a factor of 1/2. And then the other transformation in here with that negative a value, so that's its own transformation, that causes a reflection over the x-axis. So instead of the parabola opening up, it's now going to open down. So that's a reflection over the x-axis, makes it open down. And then for the last one, that plus 3 is going to move the graph, shift the graph up 3 units, which we call a translation up 3 units. In example 3, it says make a table of values to find the zeros. Again, we're looking for the x-intercepts to find the zeros of the function. So here, make a table of values. Okay, so I'm going to have an r of x table. And ultimately, what I'm looking for are x-intercepts. So that means, if I just go back to this table right here, or this graph right here, x-intercepts are when y equals 0. So I'm looking for when r of x is a 0, so if I get a 0 here, then I know that I've got x-intercepts. And again, there could be 0 of them, there could be 1 of them, or there could be 2 of them. So let's think about this. This has a minus 27. So if I just think of a rough sketch of a graph, a minus 27. So we're going to go down 27 units all the way down to here. That's where my vertex is going to be. And it has a positive 3 leading coefficient, which tells me the graph opens up. It's a vertical stretch by a factor of 3, but it's not negative. That 3 is positive, so it should still open up. So I know I'm going to have 2 x-intercepts. So just by thinking about it, that rough sketch, we know we're supposed to have 2 x-intercepts. All right, so let's start plugging in some numbers. Let's try to plug in, well, let's just start with 0 and see where we're at here. So I know if I plug in a 0, I'll get 0 minus 27 is negative 27. If I plug in a 1, I'll get 1 times 3 is 3 minus 27 is still negative 24. So I'm pretty far away from finding those x-intercepts. So instead of just plugging in a 1, how about I plug in 4? 4 squared is 16. 16 times 3, oh, that's bigger. That's going to be bigger than 27. I'm not going to get out 0, so it has to be a number smaller than 4. So let's try to plug in a 3. 3 squared is 9. 9 times 3 is 27, and 27 minus 27 is 0. So that's an x-intercept. So if I plug in negative 3 squared is positive 9, times 3 is 27, minus 27 is 0. So you can see right here and right here, we've got x-intercepts. And that's what we were looking for. These are x-intercepts. So how we're going to express our answers for the zeros of the function, it's the values of x. Let me write this on here. The values of x. Actually, I want to add this to my definition back here. The zeros of a function, it says an x-intercept of the graph of a function. That's your textbook's definition, but I actually want to change that up. I'm going to say the values of x that make y make y 0. Or I could say the values of x that make the function equal 0. Okay, so I'm looking for the values of x that make the function equal 0. So right here, the zeros are going to be those values of x that make the function 0, so that make y 0. So these are the values of x that make y, or r of x, 0. So my answers are x equals negative 3 or x equals positive 3. Those are my zeros of my function. So let's try one more here. This is the last example for this section. So find the zeros of this function. This one does not say make a table of values. So what I'm going to do instead, because finding the zeros is when y is 0, I'm going to plug in 0 for y, which in this case is a t of x, that's function notation for y. And I'm going to try to find the values of x that make this true. So what I'm going to do is factor out the greatest common factor, which is a 5. What remains is an x squared plus 25. Now, unfortunately, with this one, we are not going to be able to factor this any farther. So I was hoping that we could use the zero product property, but in this case, that is not going to work. And if I try to set this equal to 0 and solve, what's going to happen, I can just show you this real quick. If I try to set this equal to 0 and solve, I'd have to subtract 25 from both sides and get an x squared equals negative 25, and then I'd have to take a square root. And there's no way to solve this in Algebra 1. In Algebra 2, you're going to learn about imaginary numbers, but in Algebra 1, there's no number you can plug in for x and get out a negative 25 after you square it. So that's not going to happen. So that's no good. We have to find a different way if there is a different way. Let's just think about this one. So on the previous example, I did really what I should have been doing on this example. Just thinking graphically, what would this look like? Well, I have a positive 125 here. So my vertex is 0, 125. 0, 125. So I'll just go up by 25s here. That's a really rough, terrible looking graph. All right, so 0, 125. I have a positive 5 leading coefficient. My graph is going to open up and be a vertical stretch by a factor of 5. There are no x-intercepts on this one. So this is not going to happen. I'm not going to be able to find the zeros of this function, at least in Algebra 1. So in this one, what I'm going to say is the function has no zeros. If you want to be 100% correct, you'd have to say the function has no real zeros. Again, in Algebra 2, you're going to learn about imaginary numbers, and then you could say there are some imaginary zeros, but if you just say no zeros at this point, that's okay, I'll accept that. But I'm going to write the function has no real zeros. That is my answer, because again, we've got a 0, 125, for the coordinates to the vertex, and the graph is opening up. So it's never going to cross the x-axis. All right, so your assignment for this section is pages 429 to 430, numbers 3 through 12. I cut this assignment down quite a bit, so let me just go ahead and open this one up, 429 to 430. Chapter 8, 429 to 430. All right, and here we go. So your assignment again is numbers 3 through 12. In these problems, it says graph the function and compare to the parent function, and that's what you're doing in all of these. Now that I'm looking at this, I don't know why I cut out so many of the other problems because those are good problems. I'm going to change this up a little bit. So what I'm going to do is not assign just 3 through 12 because that's just all graphing, which is practice, especially from what you were doing in the last section. So I'm going to change that. I'm going to go with 3, 5, 7, and 9. So I'm cutting out a bunch of the graphing. And then instead of cutting out the other problems, let's go with I need some here where you're finding the zeros of the function. So let me see which ones of these would be good. I'm going to start with number 19. That's 19, 20 is good. 23. Actually, like a lot of those. I'm going to go 19 through 20. 19 through 20. Actually, I'm going to change that and go 20 through 26. I'm going to make that evens. So you have 4 problems there. And then I do like number 28, and that will be your last problem. So this is so much shorter than it used to be. I don't know why I cut out so many of them, but this really is a good assignment for this section. So if you have any questions, please let me know. I am going to go through one question with you. The graphing and then comparing to the parent function I covered in the lesson, so I'm not going to go through any of those in this. 20 through 26, you are finding the zeros, which again, you should start by thinking about where that vertex is, and then is the graph opening up or down, and that way you can figure out how many zeros you have before you actually go on to find them. So that's what I did in the 2 last examples of this lesson. We can briefly talk about number 28 though. So number 28, it says that the function y equals negative 16x squared plus 36 represents the height in feet of an apple x seconds after falling from a tree. So x is the time in seconds, and y is the height in feet. And again, it's the height of the apple falling from that tree. All right, so it says find and interpret the x and y intercepts. Okay, so you've been doing this for a very long time, for years now. To find an x-intercept, you plug in 0 for y. I'm going to type that out here. To find an x-intercept, you plug in 0 for y and solve. And then to find a y-intercept, you plug in 0 for x and solve. So you've been doing that since middle school, so that's nothing new there. Woo. All right. So what I'm going to do is start by finding the x-intercept. And again, to find an x-intercept, you plug in 0 for y. Just briefly thinking about what this graph looks like, I have 0, 36 for the vertex, the coordinate 0, 36. It's opening down, and it's a vertical stretch by a factor of 16. So I know I'm going to have some x-intercepts because my vertex is at 0, 36, and the graph is opening down. The parabola opens down. All right, so to solve this one, I'm going to, well, you know how to solve, we can actually solve these equations by just subtracting 36 from both sides. I get negative 36 equals negative 16x squared. Divide both sides by negative 16. So negative 36 divided by negative 16, the negatives are going to cancel. 16 goes into 36 two times. That gets me to 32, and I have 4/16 left over. Now to undo that square, I would have to take a square root of both sides. First, let me simplify this a little bit. That is 2 and 1/4. If I want to get the x by itself, square root both sides. Now the square root of 2 and 1/4, 2.25. If I take the square root of that, I get 1.5. But remember, when I take the square root of a variable squared, I could plug in a positive or a negative and square it to get out a positive. So I need to consider both options. So I need to take the absolute value of x. So the square root of a variable squared is equal to the absolute value of that variable. So that equals 2.25. Oh, excuse me. I just took the square root. That equals 1.5. All right. So again, the square root of a variable squared is the absolute value of x. On this side, the square root of 2.25 is 1.5. And to solve this equation, the two values I could plug in for x to get out a positive 1.5 are a positive 1.5, because the absolute value of positive 1.5 is 1.5, or a negative 1.5, because the absolute value of a negative 1.5 is positive 1.5. So my two solutions here are going to be negative 1.5 or positive 1.5. And again, we knew we should have two x-intercepts because we're at positive 36 for our c value here. So 0.36 is the vertex. It's opening down. So you're way up at 0.36 and the parabola opens down. We know we should have two x-intercepts. All right, so there's that. Here it says find and interpret the x and y intercepts. So my x-intercepts, if I write these as points, are negative 1.50 and positive 1.50. We'll interpret those in a second here, but first I want to find the y-intercept. So to find a y-intercept, starting to run out of room in this. To find a y-intercept, as I wrote before, you need to plug in 0 for x. So y equals negative 16 times 0 squared plus 36. Well, that cancels out here. 0 squared is 0 times negative 16 is still 0. So we get y equals 36. So the y-intercept is 0.36, which is also the vertex. All right, so I have my x-intercepts, I have my y-intercept. Now again, just think of this graphically real quick here. So we've got 0.36. Let's go up by 6 on my y-axis. 0.36. We have two x-intercepts, negative 1.50 and positive 1.50. So my graph looks like this, just as a rough sketch. And it says we need to interpret the x and y intercepts for this problem. Again, x is the time in seconds. So this is the time in seconds for the height of an apple. And here at 0 seconds, 0 seconds, because x is the time in seconds, we have a height of 36 feet. So what that means is that apple starts at 36 feet. It's a tall apple tree. Yeah, I don't think these authors know much about apple trees because I was curious. I just looked it up. The tallest two apple trees found in Germany were 12 meters and 11 meters. We have one in France that was 11 meters. And those are just above 36 feet. But after that, you're below 36 feet. So yeah, I guess we're talking about the tallest apple trees ever. Nice. All right. Anyway, so what this means at 0 seconds, that apple's at 36 feet for a height. So what I'm going to say for my answer here, the apple starts, I need to make this smaller. The apple starts at a height of 36 feet. So that's the y-intercept. And then to interpret the x-intercepts, well, again, the x coordinate on here is time. Can we have a negative time? No. So this answer does not help me in this word problem. Only this one makes sense. So at 1.5 seconds, the height is 0. So what does that mean for a falling apple? That means it takes, or it took, I suppose it's already fallen, it took 1.5 seconds for the apple to hit the ground after falling. So at 1.5 seconds, it has a height of 0. That means it hit the ground. 1.5 seconds, it hit the ground. All right, so this right here is my answer. And I'm going to be giving you some more problems like this down the road, so I wanted to walk through this one with you, but what I highly recommend is that if you've been copying this down and following through with me, that's great. I highly recommend you cover this back up at some point in the next day or two and try this problem on your own again. I will be giving one like this similar on the quiz, and you're going to be seeing a lot of problems like this in Algebra 2 as well. So please, if you could, try this one again on your own. All right, so that's all I have for you for today. This assignment is going to be due by 11:59 p.m. on Tuesday evening. All right, thank you.